All right, just when you thought it was safe, I'm back. Okay, so let's continue. In that first installment, I introduced you to mechanical energy. Just a quick review. Mechanical energy and defined potential and kinetic energy. I introduced you to the potential energy equation today just so that I could point out that the height is what makes a difference. Yes, mass makes a difference, but relative to how much energy, potential or stored energy something has relative to the Earth really is dependent on the height and the mass. But in this case, I wanted you to really understand, or I wanted to highlight the importance of the height variable. Okay, so I'm going to introduce you to kinetic energy, and I'm going to show you the equation, but we're going to learn how to calculate it tomorrow. We'll push that back. But I'm going to show you the equation so that you can see the variables that impact how much kinetic energy something has. So we've defined kinetic energy as the energy of motion. Something has to be moving. And that's where we started our whole study of physical science, was with motion, defining motion, calculating motion, and then understanding that there had to be force in order for motion to occur, and how much energy is required, or the energy of that motion now we are referring to as kinetic energy. Okay, so kinetic energy mathematically is 1/2 mv squared. And again, I'm going to teach you how to manage the equation tomorrow, and we'll do some calculations with this tomorrow. But right now, I'm sharing it with you so that we can see, again, that mass impacts how much energy of motion we have, but also velocity. And notice that that velocity is squared. So the definition of kinetic energy is the energy of motion, i.e., something has to be moving. And how fast it's moving dictates the amount of kinetic energy that we say it has. Okay. All right, so energy of motion, energy of position, or stored energy. And I started this by speaking to you about mechanical energy, the energy that is due to position and the motion of an object. So now we want to relate those. So mechanical energy, which we'll refer to as ME, let me write that out. Sorry. Is equal to the sum of kinetic energy and potential energy. So how this plays out and the way that we want to analyze it today is I'm going to use an example of a pendulum. All right, so I've got a pendulum, ball on the end of my pendulum. So I'm going to say this is my midpoint. So the pendulum had to be pulled back, and this is going to be the lowest point of the pendulum. So when I raise the pendulum, let's say I've raised it to this position. Let's say it has a total of, and I'm holding it. I'm going to draw a poor image of a stick person as if they're holding that pendulum. So they pulled it back and they're holding this pendulum. And let's say that in this position, it has 50 joules of energy. The question becomes, what kind of energy is it? So we're considering mechanical, kinetic, and potential. So what we know is that the sum of the kinetic and the potential is what we refer to as the mechanical energy. So in other words, my real question here is, when they are holding the pendulum, is the energy kinetic or is it potential? So if they're simply holding it and it's not moving, then it's the energy of position. We're having an announcement. It's the energy of position, right? Because the I don't know what that was. Because it is at some height from its lowest point. Okay. So this is potential energy is 50 joules. Now we've said that the sum of kinetic and potential is the mechanical energy. How much kinetic energy does this pendulum have at this point? If it's not moving, meaning it has no velocity, then none of the energy in that system is kinetic. Mechanical energy is the sum of the kinetic and the potential. So how much mechanical energy is in this system? 50 joules. So let's say they let it go and it tracks to about right here. Imaginary. Okay. So let's pretend, because that's poorly illustrated, let's pretend that that's halfway, the halfway mark. Okay. So if it's halfway, we can say, and it's moving. Okay. So when it reaches the halfway point in its motion, goodness, then we can say it has 25 joules of kinetic energy. How much potential energy will it have? 25 joules. How do you know, Ms. Kyle? Because the total energy of the system, the mechanical energy, is not going to change from 50. You can't put in any more than you started with. So when it reaches this lowest point, let's say it's right here, reaches its lowest point, this belongs here, then if we let it go, it will be traveling its fastest at its lowest point. So the kinetic energy is going to be 50 joules. The potential energy, it's at its lowest point, so it can't go any lower. So the potential energy is going to be 0. And the sum, the mechanical energy, stays the same. Okay. So this is what we're exploring today, these relationships of potential and kinetic energy relative to the mechanical energy of a system. Okay. So I want you to look at that a couple of different ways. I'm going to look at a few more examples with you. And then your exercises today are going to be determining whether energy is kinetic or potential, as illustrated in a scenario. And then you'll have some problems that are similar to this, where you have to determine the mechanical energy. So based on what's given, you have to determine how much is kinetic, how much is potential. Okay, so let's look at a couple of other examples before I set you loose. Okay. So I'm going to share this document with you. And on the document, it tells us that the key to locating the highest potential energy is to determine where an object is at its highest location, right? So that, again, is why I shared with you, that's why I shared with you the equation, that potential energy is mass times gravity times height, because height, based on what they're just saying, the highest location is where we're going to have the most potential energy. Okay. All right. So then it advises us to look at the half pipe to the left. The skater's at its highest location. So when he starts, he's at the highest point. Therefore, his potential energy is the greatest. Whenever his potential energy is the greatest, his kinetic energy is going to be the least, because, again, mechanical energy is the sum of the two. When he comes down the half pipe, at the very bottom, he's going to be traveling the fastest. Man, and if we were in class together, I would have you do an activity to measure that. I may see if I can have you construct that at home. When he comes, just so I could prove that point, because it's, for whatever reason, not intuitive. At the lowest point, he's traveling the fastest, and he has the least potential energy. The other way to look at that is that he has the least potential energy because he's at the lowest point. And again, potential energy is contingent on the height. So based on that, we're going to look at these other scenarios. So I just walked you through a pendulum swinging scenario. So here it's asking you to label each location with the highest kinetic energy and the lowest kinetic energy, highest potential energy and the lowest potential energy. So based on what I just did with you, this point, if it's moving, this is the highest potential energy, the lowest kinetic energy. This would be the highest kinetic energy, the lowest potential energy, right? I'm going to actually post this one and have you consider the rest of these and give it back to me just to see how your minds work. So you've got several different scenarios where all you'll be doing is putting in, just like they've marked here, what the highest potential energy is and what the lowest potential energy is. The other thing that I'm going to have, the other two things that I'm going to ask you to do today are just like the scenario that I just ran you through, where I showed you, let me hide my, sorry, where I walked you through the relationship of kinetic and potential and mechanical energy. I'm going to ask you to use that principle to answer these questions. So here they give you the mechanical energy. So if you know the total mechanical energy, can we find the kinetic and potential? Yes. So they've told you that the potential energy right here is 0 joules. If I know the mechanical energy is 15 joules, I can find the kinetic energy at this spot. So I'm going to ask you to do number 1, number 2, upside down, and number 6. We're going to save the actual mathematical calculations until tomorrow because, again, I'm noticing on your tests that the calculations are where we're bumping into, we have some trouble with the calculations. So that, to me, is for one of two reasons, maybe three reasons, but one is that you aren't doing enough, you don't understand how to apply the equation, and or two, you're not doing enough practice to feel comfortable applying the equation. Okay, so I'm going to help remedy number 2 by making us do a little more practice, and I'm going to assist us by requiring that we do the problems or solve the problems a particular way. Because I know in my experience, which we haven't met, so you don't actually know me, so I've been teaching for 15 years. In my experience, that following the process, learning the process step by step, is going to help you tremendously and reduce the probability of you getting the answer wrong significantly. So I'm going to help you build that skill of problem solving in a particular way. And then finally, what I'm going to ask you to do is look at this sheet. And again, here, all you're doing is determining whether the energy that's presented in the situation is kinetic or whether the energy that's presented is potential. Okay. Please let me know if you have questions. I'm going to post what my office hours are today, tomorrow, and Thursday. So let me know if you have questions. You will have a daily quiz on this tomorrow. But given the timing, again, I'll adjust the timeline accordingly. All right. Hope everybody has a great day.